Thank you to the organizers for the opportunity to talk and organizing this conference, and thank you everyone for coming to the last talk on Thursday afternoon. So the big idea, I should say, this is joint work with Ilani, Axelrod-Freed, Judy Chiang, Patty Commins, and Veronica Lang. Okay, and so the big idea of what I want to talk about today is that I want to study sort of an interesting but mysterious Markov chain using techniques from combinatorial representation theory. So what I'm going to do is I'll tell you about the original Markov chain, which is called random-to-random shuffling. So it's a type of card shuffling. And then I'll tell you about how we Q-deform that process to give it richer structure. And then I'll tell you about sort of what we study about this, which are the eigenvalues of this process. So this has probabilistic motivation because eigenvalues tell you about how the Markov chain behaves. But it also has combinatorial motivation because the eigenvalues turn out to have really nice integer, or in the Q analog case, polynomial formulas. Okay, and so here is a preview of what I'm going to say. The rest of the talk will basically be explaining what this slide says, so it'll make more sense in a little bit. But the main idea is that the eigenvalues of this Markov chain in the Hecke algebra will be satisfy this formula, so they'll be indexed by horizontal strips. And so in particular, they're all going to be polynomials in Q with non-negative integers. And our method, so I think Jonathan Novak in his talk sort of gave an endorsement for the Kunkov-Vershik approach to representation theory of the symmetric group and the Jucys-Murphy elements as a way to get at that theory. And I will give another endorsement of that perspective and also say that it generalizes really beautifully to the Hecke algebra. So it's useful in that world as well. Okay, so what are we doing? So I'm going to define this process random to random. I have a deck of cards, and I pick a card at random with uniform probability, and I move it to a new position with uniform probability. So for example, if I have, if I have 3 cards, let's say I pick card 2, so that's like the first card I pick, and now I move it to a new position. So sorry, I'm used to a different clicker. Okay, let's say, and then I move it to the 3rd position here. Okay, and so this is like one wet thing I could do. And the question is, if I wanted to shuffle my deck of cards in this way, how many times would I actually need to do it to make sure that I have a well-mixed deck of cards? Okay, so formally, what I'm going to think about is the deck of cards is going to be a permutation in one-line notation. And I want to think about random to random as an element of the group algebra of the symmetric group that acts on permutations by right multiplication. So I can think of it as a map from the group algebra to itself. And what it's doing is I take my permutation, sigma, and I want to think about I move a random card, like in position I, to the front of my deck. Okay, so that's what this is doing. I'll call it random to top. And then after I have it in the front, I'll move it to a new random position J. So these SIs are adjacent transpositions. So the way this will give me a linear combination of permutations, and the way you should read that is the coefficient of tau tells me the probability that if I start at sigma, I'll get to tau. So I'll do an example. Okay, so here is an example. Let's say I want to shuffle the permutation 1, 2, 3. Okay, so the first step is I move sort of 1, 2, and 3 to the beginning in all possible ways. So that's what's happening here. I've moved 1 to the top, 2 to the top, and 3 to the top, but I still have to do my second step. So that's this. Okay, and this is what step 2 is doing. So here, I've moved 1 to the first position, second position, third position, and similarly with 2 and with 3. Okay, so when I sum up all the like terms, this is what I get. And so the way I would interpret this is like 1, 2, 3. The probability that I start at 1, 2, 3 and get to 2, 1, 3 is 2/9. Okay? Okay, and so probably a lot of people are familiar with this, but so that we're all on the same page, I can encode this in a probability matrix. So the rows and columns will be indexed by the states. In this case, that will be permutation. So it'll be an n factorial by n factorial matrix. And the j or the ij entry tells me the probability if I start at state j and go to state I. So for example, if n is 3, we've already figured out one column of this matrix. So this is the 1, 2, 3 column here. I just insert it right there. OK, and I could do the rest of this matrix if I wanted to. So I'm going to pull out the 1/9 so that my matrices are all integer. And in general, I'm going to present the eigenvalues that are not normalized. But if you want to normalize, just multiply by n squared. OK. So our initial question was, if I want to shuffle via random to random, how many times would I need to do this? And the upshot here is that the eigenvalues of that probability matrix tell us the answer to that question. So the goal that I, as a combinatorialist, want to think about is actually figuring out what these eigenvalues are. So this is an n factorial by n factorial matrix, so it gets really big. And it turns out to actually be a really hard question. So finding the eigenvalues of this process was an open problem for almost 20 years. It was solved by Dieker and Saliola in 2018, who showed that these eigenvalues are actually non-negative integers. So that's surprising because there's kind of no reason to think that that would happen. And then using that information, Bernstein and Nestoridi were able to figure out the cutoff behavior. And I'll tell you what these formulas are in a second. Yeah?
So were they conjectured to be non-negative integers, or was it like a byproduct of the proof?
That was the conjecture, was that they were non-negative integers, yeah. OK, so why might we want to study this process? Well, first of all, it's an example of what's called a symmetrized shuffling operator. So this was introduced by Reiner, Saliola, and Velker. It's a type of Markov chain that's like a product of a sort of nice Markov chain and its transpose. So this M, we sort of understand all the eigenvalues. But when we take the symmetrized version by multiplying by the transpose, we lose all intuition. We basically don't understand anything, except in the case of random to random. So random to random is the only example in this family that we understand. And you should think of like this M was that random to top, and then the M transpose is the top to random. From a combinatorial perspective, it has a lot of interesting connections to things that are really nice combinatorics. So derangements of permutations by work of Waterford and Uyemura-Reyes. Gessel's fundamental quasi-symmetric function by work of Desarminian and Wax. Markov chains on linear extensions by work of Ayer, Schilling, and Thierry. And in our work, we show that it is also connected to the Jucys-Murphy elements. OK, maybe a third reason is that it has integer eigenvalues, which is, in general, is like very surprising. There's no reason to expect that from a Markov chain on this form. And in fact, like most of these symmetrized shuffling operators do not have that behavior. And it has a nice Q-deformation, which I'll tell you about. And then lastly, I think the sort of methods that we need to understand random to random really involve like developing combinatorial representation theory and using that, like integrating that into probability theory. OK, questions before I sort of go to the Q-deformation? All right. So the idea here is that I want to introduce a parameter Q. And today you can think about the parameter as a probability. And I'll recover classical objects at Q is equal to 1. So the sort of most classical object that maybe exists in algebraic combinatorics is a non-negative integer. And here's its Q analog. I think we've seen this sort of a lot in this conference, but just in case. So it's this polynomial in Q. And if I set Q to be 1, I just get a sum of K1s. So I recover K. The sort of algebraic classical object that I want to think about today is the group algebra of the symmetric group. And so its natural Q analog is the type A Iwahori-Hecke algebra, which I'll define in a second. OK, so some context about studying these processes in the context of Hecke algebras. Well, Bufatov showed that many interacting particle systems that we've seen talks about can actually be viewed as random walks on Hecke algebra. So we actually have seen this before in the conference, even if it wasn't presented in this framework. And then work of Diaconis and Ram studied mixing times for Markov chains on Hecke algebra. So they've sort of initiated the study of like, once you have eigenvalues, what do you do? And if you don't like the Hecke algebra, but you prefer vector spaces over finite fields, this work actually initially started with work of Patty Commins and Vic Reiner, where we were looking at random or shuffling operators on the space of complete flags over a finite complete flags of a vector space over a finite field. So if you prefer that perspective, everything that I say could be translated into that. Yeah. Okay, so what is the Hecke algebra? Well, I want to compare it to its classical counterpart, the group algebra. So here is a presentation of the group algebra in terms of those SI adjacent transpositions. Okay, so and it's generated by S1 to Sn minus 1, subject to these three relations. And so when you look at the Hecke algebra, you should think this looks very similar. So these TIs that generate the Hecke algebra are similar to the SIs. And the relations 2 and 3 are literally exactly the same. So the real difference here is this first relation. So Ti squared is equal to this instead of being equal to 1 as it is in the symmetric group. But if I set Q to be 1, this term disappears and I get Ti squared as 1. Okay, and so this is, if you're an expert in the Hecke algebra, this is a slightly different presentation than is sort of standard in representation theory. It's the presentation that's more relevant from a probabilistic point of view, but you can recover the sort of classical presentation if you want. Okay, so how are we thinking about the action on the Hecke algebra? Well, I'm gonna act by my generators, okay, and my generator Ti will act on a word on the I and I plus first position in two different ways. So if Wi is less than Wi plus 1, so if I don't have a descent, Ti will act sort of exactly the way the symmetric group acts, just by swapping positions. But if Wi is bigger than Wi plus 1, so I do have a descent, then I get this sum of two things. And you can think about it with as probability Q, I swap, and probability 1 minus Q, I don't swap. So for example, if I act by T1 on this permutation, because 1 is smaller than 3, I just swap those two positions and it's fine. It's exactly like what happens in the symmetric group. But if I act by T2, because 3 is ahead of 2, I get the sum of two things. Okay? Okay, so this is how we defined random to random as this multiplication by an element of the group algebra. And now I want to define its Q analog as multiplication by this element in the Hecke algebra. Okay, so I've replaced the SIs with TIs, and then I also pick up a factor of Q here. Okay, and here's an example of what this would look like. Let's say I want to act on that same permutation 1, 2, 3. Okay, and I still have my two-step process. So here I first am going to do the Q random to top. So because 1, 2, 3 is in order, I don't pick up any extra terms. I just sort of have, I've moved the 1 to the front, the 2 to the front, and the 3 to the front, but now I've picked up some Qs. Okay, and then in my step 2, things get a little crazier, right? Like I pick up way more terms. And this is what it looks like when I group all the like terms. So it's small because it's kind of ugly, but what you should notice is that when I set Q to be 1, I recover what I originally had. So for example, like here, Q equals 1 makes this have a coefficient 0.
So,
yeah.
Just so that I can get something from the slide without reading all of the details.
Yeah.
You're doing the same sequence of transpositions. It's just sometimes they are lazy.
Yeah, sometimes they
so it might not anymore move card J up to the front and then back into position R. It might do a bunch of
with probability Q, it'll do that, but with probability 1 minus Q, and then it sort of cascades. So it gets very complicated. Yeah, but yeah, that's exactly what happens. Other questions? Okay. So our goal was to understand the eigenvalues, and really a secondary goal was I actually wanted to understand the eigenspaces as well, because that's sort of essential to actually figuring out the eigenvalues. And when I say describe the eigenspaces, I really mean as representations. So I'm going to sort of sweep that under the rug, but it's underlying everything here. Okay. So
quick question.
Yeah.
Was the stationary distribution already known for this?
I don't know.
Okay.
Q analog?
What?
For the Q analog?
Yeah.
Could it be Q mallows?
I don't think anyone has studied the Q analog of this before, because we sort of came to it in a roundabout way even.
Cool.
Yeah, that is my impression.
It depends on the descent, so it's not clear.
So,
Yeah. All right. So how do we understand these eigenvalues? So to describe them, I'm going to take two partitions, mu and lambda. So mu's inside of lambda, And I'll take what's called a skew tableau. So I just remove mu from lambda. And I'm going to care about special types of skew tableau that are called horizontal strips, which means that I am allowed to have at most one box in each column. So for example, this is a skew tableau, so my partition 3, 2, 2. I remove 2, 1, 1, so I get this blue shape here, but this is not a horizontal strip because I have these two boxes here. This is a horizontal strip, right? And you can see, like, if I squished it all together, it would just be one strip. Okay, so the last thing I'm going to need is that the content of a skew shape, so this statistic on skew shapes, I'm going to sum up all the rows and columns in my skew shape and take the difference between the column and the row. So for example, here, I've written in the boxes all the contents. And so I'm just, so like this is 2 because it's in column 3, row 1. And so I'm just adding up all the contents in the blue boxes, and I get 1 in this case and 5 in this case. Okay? Okay, and so what Dieker and Saliola proved is that the eigenvalues of random to top, so they're going to all be indexed by horizontal strips, lambda mod mu, where lambda is of size n. Okay, so I take all the possible horizontal strips of all partitions of size n. And this is the eigenvalue that this horizontal strip gives me. So the content of my skew shape plus this formula here. So in particular, this proves the conjecture that they were all non-negative integers. And here's an example. So let's say this is my skew shape. The content is 0 because minus 2 plus 2 is 0. When I do this formula, I get 11. Okay. And again, these are not the normalized ones, but I can normalize. Okay, and then using this information, Bernstein and Nestoridi showed that random to random exhibits cutoff behavior at 3/4 n log n minus 1/4 log of n with window of order n. Okay, and I'll say that like this formula was a little bit mysterious, even though they solved the conjecture. Like the presence of this content was not really explained. And also, like, this argument is very delicate. Like, it was a very, like, subtle and hard argument. Okay, so now I want to give you the Q analog here. And so I'm going to need a Q analog of content. And so content in general can be negative. So I need to slightly generalize my idea of Q integer to allow for negative integers. So I'm just going to have it be this rational function. But if n is a positive number, I get the same Q analog I showed you before. And the Q content is going to be the sum over, it's kind of the naive Q content. I just Qify every sum and here. So this will be a polynomial in Q and Q inverse. But if I multiply by Q to the n, it becomes like a true polynomial. Okay, so for example, if I just take the same skew shape and I look at the content, I'm now summing up these like Q numbers. Okay, and so the theorem is that the eigenvalues, in the case that the Hecke algebra is semi-simple, so I have to assume that Q is not 0 or root of unity, the eigenvalues of random to random, again, are going to be indexed by horizontal strips. And now this is the formula that they satisfy. So we have the Q content, and then we have this like Qified sum. So in particular, this is, again, these eigenvalues are polynomials in Q with non-negative integer coefficients. And, yeah.
The Q to the n term dominates whatever.
Yeah, exactly. Yeah, so this becomes a polynomial because of this.
So the number of those is n factorial. The total number of those is
Okay, yeah, so I'm sweeping some details under the rug about which horizontal strips. It's a little bit more subtle. You have to, like, this mu, the number of mu that you want has to do with derangements of mu. Yeah, or desarrangement tableau. But yeah, so we understand the multiplicity, but yeah, it's not quite like every single horizontal strip gives you an eigenvalue. Okay, I'm almost done. Okay, so the last thing I want to say is that like one thing that's exciting about this project for me is that it actually, like the method, so I don't usually like to talk about proofs in talks, but the methods here sort of draw, I think, cool connections. So connections, first of all, to the Jucys-Murphy elements of the Hecke algebra. So In particular, these Jucys-Murphy elements actually explain why you see this content in the eigenvalue expression. Like, it really comes from like the fact that the Jucys-Murphy elements are simultaneous eigenbasis for representations of the Hecke algebra and the symmetric group. And it also uses Young's semi-normal basis of the group algebra and the Hecke algebra. So again, if you're not familiar with this, what you should think is it's something related to the Kunkov-Vershik approach to represent the symmetric group representation theory, and in particular, it simplifies the Q=1 proofs significantly, so it makes it like a lot shorter. Thanks.